Imagine a machine teaching itself to play soccer, a rocket landing autonomously on a tiny floating platform, or an algorithm mastering trillion-dollar financial markets in the blink of an eye. These aren't scenes from science fiction. They're the real-world impact of reinforcement learning, or RL. In this lesson, we explore fascinating real-world examples of where reinforcement learning, or RL, is powering the most mind-blowing advancements of our time. During our exploration, it will become clear why RL is a significant leap beyond supervised and unsupervised learning, being able to solve problems that are impossible with conventional machine learning. Reinforcement learning represents a major paradigm shift in how machines learn. Unlike supervised learning, which relies on labeled data, or unsupervised learning, which looks for hidden patterns in unlabeled data, RL works through trial and error. It's like how humans learn, by experimenting, making mistakes, and gradually improving based on the feedback or results we get from our actions in the world. An RL setup typically includes an agent, which is the decision maker or controller, and an environment, which is the physical or virtual world in which the agent operates. For example, an agent could be a robot in a manufacturing context, a trading algorithm that makes buy or sell decisions, or a virtual player in a game. The environment might be a factory floor, a financial market, a video game world, or even a nuclear fusion reactor. An RL system trains an agent to interact within a physical or simulated virtual environment. The agent tries actions, observes results in the form of rewards it receives for its actions, and adjusts its future actions based on the rewards that result from its actions. And like with supervised and unsupervised machine learning, there is a mathematical optimization process that powers all of this. In RL, what is being optimized or maximized is the cumulative future rewards that the agent can achieve with all its actions over time. By focusing on maximizing cumulative future rewards, RL systems can literally plan for the future rather than just reacting to static historical data or making a decision that is only optimal for that moment. This is fundamentally different to supervised or unsupervised machine learning, where models passively analyze static training data to learn to predict, classify, or cluster information, and often need to be retrained with updated training data. With RL, the agent is literally able to retrain itself as its environment changes, or as it discovers new actions that result in higher cumulative future rewards. Before we look at some fascinating real-world examples, let's quickly cover the fundamentals of the reinforcement learning process. In an RL setup, the major components are the agent, its actions, the state of the environment, and the rewards that the agent acquires for its actions. At any given moment, the agent observes the current state of the environment. These could be sensor readings in a robotic arm, a chess game board configuration, or market indicators. The agent then chooses an action, such as moving a robotic limb, placing a trade, or making a game move. The agent receives a reward or penalty, which could be positive if the action helped achieve the long-term goal, or negative if it hindered progress. The agent updates its strategy and sequence of actions to do better next time. Because RL maximizes long-term cumulative rewards, it can avoid short-sighted decisions. The ability to continuously learn and improve from mistakes without needing an explicitly labeled dataset is what makes RL feel like the closest machine learning approach to human-like learning. One of the most fascinating aspects of RL is the explore-exploit trade-off. The agent must sometimes exploit the actions it already knows to collect the most rewards efficiently, but it also must explore uncharted territory in case there is a better strategy it hasn't discovered yet. This balancing act is crucial for RL's creativity and ability to stumble upon novel solutions. In traditional approaches like supervised learning, there is no room for creativity. There will always be one output for every input the model receives. With RL, however, agents can discover entirely new tactics on their own. Another application of RL, where traditional machine learning is unfeasible, is real-time control systems. Here, the agent must process continuous incoming data streams from various sensors, like cameras, GPS, accelerometers, or even magnetic field readers, and decide on actions that will affect future states. This makes RL an excellent fit for tasks that demand both immediate reactivity and long-term planning. An exciting development in RL is the use of world models. These are simulated or learned representations of a physical environment. World models comprehend the dynamics of the real world, including physical laws and spatial relationships. These models process diverse inputs, such as text, images, videos, and motion data, to generate predictions about future states of environments. They learn to represent and anticipate dynamics like motion, force, and spatial interactions from sensory data, enabling them to simulate realistic scenarios. By simulating an environment's dynamics, an agent can practice billions of times without real-world constraints. This approach is particularly useful for expensive or dangerous scenarios, such as nuclear fusion stabilization, rocket landings, or advanced robotics. By training in simulation, the agent refines its strategy before it even touches the physical world, similar to how a pilot might use a flight simulator to gain proficiency. Now, let's explore some of the mind-blowing achievements of RL, starting with robotics. In robotics, RL has enabled machines to learn behaviors that were once the exclusive domain of living beings. For example, robots can now teach themselves to walk, run, and even play soccer. These robots don't just mimic pre-programmed movements, they learn to adapt to new environments, recover from stumbles, adjust to uneven ground, and refine their strategies. The possibilities extend to factories, where RL helps robots optimize assembly lines, and even healthcare, where RL-driven robots assist in surgeries requiring precision and adaptability. These systems continuously read data from sensors like cameras, force detectors, and accelerometers, factoring in past experiences and future goals to choose the best action at each moment. Traditional supervised or unsupervised methods lack these real-time adaptive capabilities. Then there's the remarkable feat of landing rockets. SpaceX, a pioneer in space exploration, uses reinforcement learning to guide rockets back to Earth, landing them on floating platforms in the ocean. Think about this. The system must account for wind, platform movement, and a host of other variables, all in real time. RL enables the rocket to adjust its strategy with precision, ensuring a safe and cost-effective landing. It's a breakthrough that has transformed space exploration. Closer to home, RL powers recommender systems on platforms like Netflix and Instagram. While traditional systems often use supervised or unsupervised learning to suggest content, RL takes personalization to another level. Why? Because RL doesn't just optimize for short-term engagement, like getting you to click on one video, it focuses on long-term user satisfaction. For example, it learns the sequence of recommendations that keeps you engaged over hours, days, or even weeks. RL-based recommenders adapt to changes in user behavior or preferences in near real time. Yes, RL truly elevates personalization by going beyond static patterns, continually exploring new content to recommend while exploiting known user preferences. This dynamic adaptability is what makes RL-based systems superior to traditional recommenders, tailoring recommendations to your evolving preferences. High-frequency trading is another domain where RL's adaptability shines. Financial markets are incredibly complex and fast-paced, with conditions changing in milliseconds. Traditional trading algorithms, often based on fixed rules or supervised learning, struggle to adapt to such volatility. RL algorithms, on the other hand, continuously learn from the market itself, developing strategies that maximize profits while minimizing risks. They're not just reacting to data, they're discovering patterns and strategies that humans might never notice. Perhaps the most awe-inspiring application of RL is its role in controlling nuclear fusion reactions. Plasma control requires continuous adjustment of magnetic fields to keep the superheated plasma stable. In cutting-edge experiments, RL has been used to stabilize plasma, the superheated substance needed for fusion. Managing plasma is extraordinarily challenging, requiring constant adjustments to magnetic fields in fractions of a second. RL systems have proven more effective than any human or traditional algorithm, bringing us closer to harnessing fusion as a virtually limitless source of clean energy. And we can't forget games, a field where RL has truly captured global attention. AI systems like AlphaGo and AlphaStar have defeated world champions in games like Go and StarCraft. These systems didn't learn by watching human players. They learned by playing against themselves billions of times, exploring every possible strategy. The result? They've achieved superhuman performance, creating strategies so innovative that even experts are left amazed. The game of Go has an astronomical number of possible board positions, roughly 8 times 10 to the power of 100, making it impossible to rely solely on supervised learning from human moves. RL allowed AlphaGo to learn by playing against itself, exploring a near infinite range of strategies, and eventually surpassing even the best human players. Because of the explore-exploit trade-off, these agents don't get stuck mimicking the same existing strategies. They can invent entirely new ones, surprising even the world's top experts. Reinforcement learning is also being explored in military contexts. Robotic bomb disposal agents can learn to navigate hostile environments, adapt to changing conditions, and disarm explosives with a steady hand. Autonomous aircraft and drone swarms can be coordinated via RL to maintain formations, avoid collisions, and complete reconnaissance tasks. For swarm control, multiple RL-driven agents can cooperate, dividing tasks and adjusting dynamically to changing mission requirements. These applications highlight RL's potential for complex, high-stakes operations where adaptability and safety are paramount. In summary, what makes RL so transformative is its ability to thrive in dynamic, uncertain environments where traditional learning methods fall short. It doesn't just learn from data. It learns by doing, by exploring, and by improving over time. This adaptability makes it uniquely suited for high-stakes, complex problems where the rules aren't fixed and the environment keeps changing. From walking robots to self-landing rockets, from optimizing content recommendations to stabilizing nuclear fusion, reinforcement learning has pushed the boundaries of what machines can achieve. It's not just a tool for solving problems, it's a gateway to discovering entirely new possibilities.